Okay, this video is going to show you how to calculate the pH of a weak acid solution and also how to calculate percent dissociation or ionization of that acid. Okay, so the first thing we're going to do is we read the problem. It's talking to us about calculating pH, gives us molarity, gives us an acid, gives us a Ka. So the first thing we have to do is we have to look at the acid and we have to ask ourselves if the acid is strong or if it's weak. Now, if you don't have your strong acids memorized, you need to do it now. But if you still refuse to memorize it, what you can do is you can use a Ka. If they give you a Ka, it is screaming at you. The problem is screaming at you that the acid is weak because you won't be given a Ka for a strong acid. So if you have a strong acid, you're going to do negative log of the hydrogen ion concentration. If you have a weak acid, you have to do an equilibrium problem. So hydrogen fluoride is a weak acid. Here's the Ka for it. So what we have to do is we have to set up an equilibrium problem. So the first thing that we do is we write the reaction. So I'm going to write it plus water because I don't want you to have to worry about, do I include water with acids or bases? We're just going to write it with water. You don't have to. So we will get a hydronium ion because this is an acid. So this is a proton donor, so it's going to give the proton to water. And then we are also going to get the fluoride ion. So the very first thing you do is you write the reaction. The second thing you do is you set up an equilibrium chart. So an ice chart. I'm going to draw a fence underneath the arrow. And then water is a pure liquid. It's not included in the expression, so I'm going to X it out because it's not included, so we don't need it. We don't need to worry about it. The next thing that I want to do is I want to substitute the given information into the problem. So it tells us that we have a 1 molar solution of hydrogen fluoride. And on this line, we want to have concentrations. Notice that all you have is the weak acid and water. So this is not a stoichiometry problem. This is equilibrium. And we have none of our products initially because this hasn't dissociated yet. Okay, so what we do next is we've been given a Ka, which is like being given our equilibrium constant. So we could write an expression. So I can say that the Ka is equal to 7.2 times 10 to the negative fourth. Well, wait. I want to go back and I want to write this the way that you do it on the AP exam. So if you're asked to write the expression, we would do the concentration of, sorry, that was bugging me, that they were different colors. The concentration of our products, and they're both included because they're in aqueous solution, divided by concentration of HF only because this is an aqueous solution. We're not including water. So this is our expression. We've been given a Ka, so I have this value. I'm going to do a different color. So that would be 7.2 times 10 to the negative fourth. Now, if you remember when we did equilibrium problems, when you were given the equilibrium constant, but not equilibrium concentrations, we used X. So that's what we're going to do in our table. I don't know how much HF is going to go down by, so that's going to be minus X. Because we have a 1 to 1 molar ratio, our products go up by plus X, and then we just add or subtract down. So 1 minus X, X, and X. So I'm going to substitute that into the expression. So basically we have X times X, which is X squared divided by 1 minus X. So now I need to solve. So what we're going to do is we are going to cross multiply, which would give us, I'm going to write it up here so I have room. 7.2 times 10 to the negative fourth minus 7.2 times 10 to the negative fourth x. That's going to equal x squared. I want to get everything on the same side, so I'm going to move both of these to the side with x. So it's going to be 0 equals x squared plus 7.2 times 10 to the negative fourth x minus 7.2 times 10 to the negative fourth. Okay, now I'm going to have to use the quadratic. Okay, so after I used the quadratic formula, I ended up that the only x, I got a negative x and a positive x, so my positive x is 0.0265. Excuse me, and that would be a molarity. Okay, so if I go back and I look at significant figures, I have 3 here, and I have 2 for my Ka. So in terms of sig figs, it's not really asking me for concentration, so I don't need to do that right now. But I'm going to go ahead and do it because we need to practice it. So 1, 2 would be 2.7 times 10 to the negative 2 molar. Now that X is for fluoride concentration and hydronium ion concentration. I could also do 1 minus that to get the concentration of hydrogen fluoride at equilibrium, but I don't need to do that right now. So now what I want to do is I want to calculate pH. So to do that, let me get rid of my Ka, my equilibrium expression. So now I have the hydronium ion concentration of this weak acid. So I'm going to do the negative log of that, which is this answer right here, 2.7 times 10 to the negative 2. Okay, I want you to notice that if this were a strong acid, the concentration of the hydrogen ion would be, or hydronium ion would be 1, but because it's a weak acid, it's much less. So I'm going to do negative log of that value, and sorry, I didn't already solve it. Negative log of 2.7 times 10 to the negative 2. Whoops, I did that wrong, sorry. And I get 1.57. Excuse me, I need to pay attention to significant figures. I have 2 significant figures here. That tells me 2 numbers after the decimal. So 1.57 is correct, and that makes sense. A pH below 7 for an acid, even if that acid is weak, that makes sense. Okay, so I'm going to do one more example. Okay, here I want pH and I want percent ionization this time of a 0.02 molar solution of benzoic acid. So the first thing I do is look at benzoic acid. I ask myself if it's strong or if it's weak. It is weak. I know that because it's not part of our little hyperhickel high, honohickel low, H2SO4 chant. Plus, I'm given a Ka, so that's another clue that it's weak. So because it's weak, I must do an initial change final table, so that's what I'm going to do. I'm going to start by writing the reaction. So benzoic acid is C6H5COOH, and I'm going to write that plus water. Now remember, this is that carboxyl group, functional group for a carboxylic acid, which is an organic acid. So when you have organic acids, the hydrogen that's at the end, not one of them that's associated with the carbon chain or the benzene ring here, is the one that's lost. So this hydrogen is the one that goes to form hydronium. And then you are left with the benzoate ion, which basically is take that hydrogen off and make it a negative because you've lost a proton. So that's your reaction. We're going to do initial change equilibrium. We're going to draw the fence. We're going to X out water because water is a pure liquid and it's not included in the expression. So then what we're going to do next is we're going to include our molarity of benzoic acid. And both of these products are at 0 because initially before this dissociates we don't have any. I am given a Ka, so I can write the expression. So the Ka is equal to the concentration of hydronium ion times the concentration of the benzoate ion. And remember that you're typically getting a point for writing this, and so that's why we practice it this way every single time. So there's our equilibrium expression. Because I actually have a value for the Ka, tells me that, and I don't have any equilibrium concentrations, tells me I've got to use X. So I don't know how much this goes down by because it's a weak acid, 1-to-1 molar ratio, so these go up by 1. And then I just add or subtract. So 0.020 minus X, X, and X. Okay, so now what I want to do is I'm going to go ahead and substitute into this expression. So I will have 6.3 times 10 to the negative 5th equals X times X, which is X squared, divided by 0.020 minus X. Okay, now we can do something special here, and the reason that we can do that is because our Ka is so small, and we mentioned, maybe we didn't even tell you, that we can do something called approximate when we have really small equilibrium constants. So the rule for this is that if our equilibrium constant, like our Ka or Kb, times 100 is less than our initial concentration, and that initial concentration would be this, then we can approximate. And I'm going to show you how to do that. We're also going to show you again in class. So if I take our Ka and I multiply this by 100, I'm going to get 6.3 times 10 to the negative 5th. That would be 1, 2, 3. That would be this number right here. So if I compare that to our initial concentration, this is much smaller. So what that tells me that we can do is that X is going to be so small that when we do significant figures, approximating, the difference we're going to get in our answer when we approximate is negligible. So what that means is that you can take the X that is added on or subtracted off that initial concentration, and you can say this is so small that it's almost like it's 0. Now, for some of you that are purists, you're not going to like this, and you can still use the quadratic formula to solve. The reason I'm showing you this is because it's much faster, and it makes the math a whole lot easier. So if I make this X 0, then what I will have, let me switch to a different color for this next step, is 6.3 times 10 to the negative 5th. That will equal X squared divided by 0.020 minus 0, which would really just be 0.020. And we can do that because our Ka is so small. If you ever see a Ka that's 10 to the negative 5th or smaller, so like 10 to the negative 6th, negative 7th, or a Kb that's that small, that's typically a clue that you can approximate, and then you want to look and just double check and make sure that you can actually do that by checking your initial concentration. So I would never want to make the X here a 0, because then it would be undefined. Maybe not. I don't remember what it is with math, but basically we're not going to be able to solve for a value for X. So it's always the one that is added on or subtracted off. So if I know that this is true, then what I can do is I can say 6.3 times 10 to the negative fifth times 0.020. That gives us, let's go to a different color, 1.26 times 10 to the negative 6. That equals x squared. So I'm basically taking the square root of both sides, and when I do that, I get 0.0011 molar. Okay, this has two significant figures. My Ka has two significant figures. My initial concentration has two, so I'm good. Okay, so that tells me that's the concentration of the hydronium ion and the concentration of the benzoate ion. So I can calculate pH. So my pH is equal to the negative log of that value, because it's my hydronium ion concentration. So if I do negative log of that, I get 2.9498. 2 sig figs, that tells me 2 digits past the decimal, so 2.95. And that makes sense for an acid. Okay, now I'm asked to do one other thing. I'm asked to calculate percent ionization. So what I want to do is I'm going to erase the pH work that I did down here. We need our X. We need to know what that is, but we don't need everything else. So let's get rid of that. Okay, so I'm going to actually write this X here. Sorry. This is 0.0011. This is 0.0011. Okay. And that's 0.0011. Okay, so now to calculate percent dissociation, what I do is I'm still taking the part divided by the whole. The part I care about is the part that makes the acid the acid. So basically the hydronium ion or the hydrogen ion divided by the initial concentration of the acid. So initial acid concentration. And then I'm doing times 100. So what I'm doing here is I am taking my X, this, I'll do a different color so you know where it's coming from, right there, 0.0011. I'm taking my initial concentration of the acid, 0.020, and I'm multiplying that by 100. So 0.0011 divided by 0.020 times 100 gives us 5.5% dissociated. Okay, so if we think about this, if we had a strong acid, that would be 100% dissociated. So 100% of this initial concentration would be over here. But we have a weak acid instead, so it's only partially dissociated. So what this number right here is telling me is that only 5.5% of this acid is dissociating into ions. So I have 5.5% ions, and I would have 94.5% undissociated acid.